Hello guys, so today I will just discuss to you the chapter 4 of Hibbeler Structural Analysis 8th edition. So in my previous videos, we are done with statically determinate thrust. So now we will go to chapter 4, which is internal loadings developed in structural members. So the coverage of these chapters will be focusing on the internal loadings. Then the other one is creating shear and moment function. Then followed by diagram. Then later on is by using the superposition method. So let's start with some kind of introduction. So before structural member can be proportioned, it is necessary to determine the force and moment that act within it. In this chapter, we will develop the methods for finding those loadings at specified points along the member's axis for showing the variation graphically using the shear and moment diagram. So maybe we will cut this video because it may take long to cover all this one in one presentation. So I will try my best to just do it I will cut it into a separate videos maybe. So here we will go to internal loadings at a specified point. As we discussed in the previous section, the internal load at a specified point in a member can be determined by using method of joints. In general, this loading for coplanar structure will consist of a normal force N, shear force B, and bending moment. It should be realized, however, that this loading actually represents the resultant of the stress distribution. So in other words, in this topic, in able to see the internal loading, we need to cut a certain point wherein we can determine the shear in the moment. Okay, so we have here the sign convention. So before presenting a method for finding the internal normal force, shear force, and bending moment, we need to establish a sign convention to define their positive and negative values. But again, this is sign convention only. Okay, so on the left hand face of the cut member, the normal force N acts to the right and the internal force V acts downward, and the moment M acts counterclockwise. So here in the figure, if this is the original member, if you consider original member and when you cut it, considering the left portion, you have normal force going to the right, then shear going down, and moment is counterclockwise if you consider the cut section here. But if you consider here, okay, so meaning when you separate a single member to say the internal loadings develop, whether it is moment, shear, or normal force, this will be our convention. Positive shear, positive normal tends to elongate. Positive shear tends to rotate the segment clockwise. And a positive bending moment tends to bend the segment concave upward. Okay, that is the definition of how we define the convention. So this shear B tends to rotate clockwise. This M tends to bend the segment concave upward, and N tends to elongate. So, did you see the effect of normal force? If we consider normal force only, it will tend the member to elongate. If we consider shear, it will tends to rotate the segment clockwise, going like this. And the moment tends to create a segment concave upward. Okay? So the following procedure provides a means for applying the method of section to determine the internal normal force, shear, and bending moment at a specified location in the structural member. So support reaction before the member is cut or section, it may be necessary to determine the member support reaction. So therefore, before you proceed to cut or to section a certain member, you need to determine first the support reactions, because this will be the basis in calculating each internal member. Okay, we cannot create or we cannot solve any internal loading without support reaction. Then number 2, we need to have the free body diagram. Keep all distributed loadings, couple moments, and force acting on the member in their exact location. Then pass an imaginary section through the member perpendicular to its axis at the point where the internal loading is to determine. Meaning, as it is, you consider the same loading, whether it is there is a couple, there is forces acting on the member in their exact location. No need to no need to modify it. Okay. Then pass an imaginary section. So, for example, if you already identify where you need to know the internal loadings, just draw an imaginary line. Okay. Then whatever the loadings originally, do not change or do not modify it. Okay. Then after the section is made, draw free body diagram of the segment. You can now put or indicate the unknown resultants: N, normal force; B, shear; M is the moment in their positive direction. Then the last one is the equation of equilibrium. Moment should be sum at the section about axis that pass through the centroid. We all know this one already, the procedure on how to make or how to use moment. Okay? Meaning, when you cut a certain section, consider the free body diagram, the reaction, and of course the direction. Always you assume that the moment will act at the centroid of the member's cross-sectional area. Okay? So meaning, for unknown N and B, you can eliminate it, right? Then you can solve directly from moment. Any unknown reactions that will pass through the moment arm will be cancelled and it will be equal to 0. So here you can determine immediately the moment. So let's have here example. So the building roof shown in the photo has a weight of 1.8 kilonewtons per meter squared. Okay, building roof. So here, this is the roof. Then you have here supported by 8 meters long simply supported beam. Okay, that are spaced. So here, these are the beams. All beams, internal beams carrying 7.2 kilonewton, while the end beams carrying 3.6. Okay? So all beams are spaced by 1 meter. Each beam shown in figure 4-2b here transmit its loading to 2 girders. This girder, front and back of the building. Determine the internal shear and moment in the front girder at point C here. So what will be the internal shear and moment, okay, at this point? Neglect the width of the the member. Again, we have roof. Okay? The roof is on top of this that has a weight of 1 kilonewtons per meter squared. And this beam carrying this load 3.6 and 7.2. Okay? Then this is the girder. So it says here that there are two girders located at the front and back. So one here and another at the back, another. Okay? So one here and one at the back. I hope you imagine, So the roof of loading, the roof of loading is transmitted to each beam as one-way slab because L2 over L1, length 2 is 8 meters and length 1 is 1 meter. Okay? So the tributary loading on each interior beam is therefore 1.8 kilonewtons times 1. So the two edge beam support 0.9 kilonewton per meter. And the reaction of each interior beam of the girder will be 1.8 kilonewton per meter times 8 over 2 is equal to 7.2 kilonewtons. 1.8 times 7 plus 0.5 plus 8. 1.8 times the length 8 divided by 2. This will be 7.2. Okay? Again, this is the girder. You have a beam. And each beam has a length of 8. 8 meters here, 8 meters, 8, 8, 8, 8. Then at the back, there is another girder. So here, we all know that this is 1.8. How did we calculate this 1.8? Originally, it's 1.8 kilonewtons per meter squared. But we all knew that the roof loading is transmitted to each beam as one-way slab. Right? Meaning, if we consider this one beam here, this one carries this load, considering 0.5 and 0.5. How much is it? 1 meter, right? 1 meter. And the length, the longer length somewhere there is 8, right? So L2, which is 8, and this is 1, it will become one-way tributary loading. So, to determine the load that will act on this beam, it will be 1.8 kilonewtons per meter squared times 1. Right? Times 1. To become 1.8 kilonewtons per meter. So now, the free body diagram of the girder is shown in figure 4-2A. So 2 times 3.6 plus 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11 times 7.2. Okay? Divided by 2 is 43.2. So the total load carried by this column is 43.2 kilonewtons each. Okay? So again, maybe some of you are confused. We will have some recap again. This beam carrying a roof which has 1.8 kilonewtons per meter squared. But if you consider this beam will carry the half of this one and the half of this one. Therefore, this beam carries 1 meter by 8 meters length. Okay, and to become distributed the load that will be carried by this beam, it will be 1.8 kilonewtons per meter squared times 1 meter, so that the load that will act is 1.8 kilonewtons per meter along this side. So here, this one is this one, right? This one is another at the outer side. It's like that So there is another 7.2 here. So that will be the load 7.2. So that we can determine that this is 7.2. This is the calculation how we come up with 7.2 kilonewtons coming from this one. Okay? So to determine the internal shear and moment, we already determined the support reaction. Now we can go to the free body diagram. So point C, you put an imaginary line, pack. Okay? So here, this is the sign convention, shear and moment. Okay? So to determine the moment, you can have summation moment at point C. Okay? Or if you want to get the shear forces at C, you can have summation forces along Y. So summation force along Y is 0. So 43.2. Okay? Minus 3.6 minus 7.2 minus 2 times shear is 25.2 kilonewtons. Then summation moment, we assume that clockwise will be positive, so moment is 30.2 kilonewtons per meter. Where did I get this 43.2? I got it from this one, this one. It's simply 7.2 times 11 plus 3.6 times 2 divided by 2 will be 43.2 kilonewtons. So now, the internal shear will be 25.2 kilonewtons and the internal moment will be 30.2 kilonewtons per meter. So if you have some questions about this one, because it's really difficult to just explain this one without really a computation with my hand. So maybe we can upload another video to explain further this one. Okay? But this is simple. So another example, determine the internal shear and moment acting at section passing through point C. Okay. What is the procedure? First, you need to identify the reaction. Okay. After you have the reaction, you can now draw the free body diagram wherein you perform the you cut where does the internal forces or internal shear, internal moment. Then lastly, you can now use the equation of equilibrium. So here you can determine the reaction, either this reaction at A or reaction at B. A is a pin support, B is a roller. So since we want to determine the internal shear and internal moment at point C, I think it will be ideal to cut here and consider this section. Why? Because it will be easy for us to determine the shear and moment considering that this is triangle. Okay? Because if we consider this one, when you cut this one and consider this one, the loading will be trapezoid and it will be laborious to do that. to determine. Although it's possible, but for simplicity, it's better you cut this one and consider this section. So first, you need to determine the equivalent load of this distributed load. So it will be it will be 1/2 times 3 times 18. It will become 27 kilonewtons, right? 27 kips, right? This is triangle loading. 1/2 18 times 3 is 27. Okay. Now, to consider AC, I consider this portion at point C. If I will cut this one, what will be the distributed load here? You can do ratio and proportion. How? WC over 6 is equal to 3 over 18. WC will become 6 over 18 times 3. It will become 1 kip per feet. So here, the value of at point C is 1 kip per foot. Okay? So you can now determine the internal the internal shear and moment at point C. Summation forces along Y, it will be, first you calculate the equivalent load of this one. Okay? 1/2 6 times 1 is 3. Okay? So 9 from this reaction, 9 minus 3 is equal to 6. Then moment will be 9 times 6. Right? So this is against the assumption, it will be negative. Negative 9 times 6 plus the equivalent load times the moment arm, 3 times 2, it will become 48 kip per feet. Okay? Let's have another example. This one. The 9K force is supported by the floor panel DE, which in turn is simply supported at its end by floor beams. These beams transmit their loads to the simply supported girder AB. Determine the internal shear and moment acting at point C in the girder. So here, you have 9K force that acts on the floor panel DE, but you have here 4 panels and supported by girder AB. Okay, so we want to determine the internal shear and moment at point C. So first, you need to identify the reaction. By the way, this is simple. So you isolate this one, the DE here. This is 9. What will be the reaction? It will be 6 times 3. How? 9 times 4 divided by 6 is 6. 9 times 2 divided by 6 is 3. And to check that one, 6 plus 3 is 9. 9 is equal to 9. Okay, so this load 9 is carried by the internal forces at DE, which is 6 and 3, which should be also the same with this I-beam to be 6 and 3, 6 and 3, 6 and 3. Okay, so now the effect or the load computed from this 9K force, 9 kip force, will be at point D and E. It will become 6 and 3, which is 6 and 3 at point D and E is 6 feet and 12 feet, then 24 feet the total length. Now, to determine this reaction, you can simply get the summation forces a moment at point B. So that 3 times, this is 6. 3 times 6 plus 6 times 18 divided by 24 is 3.75K. Here is 6 times 12. plus 3 times 18 divided by 24 is 5.25. Okay? So now, if you have the support reaction, you can now proceed to applying a cut section at point C. So here, point C, located at 15 feet. Okay? Here, this is location here, somewhere here. So 312, then the same procedure. Summation forces along Y upward is positive is 3.75 minus 6 minus BC. BC is 2.25 kips. Then moment 3.75 times 15 minus 6 times 3, it will be 38.25 kips that fit. So if you have some questions, just message me in my email. Email or messenger. Now we can go to 4.2, which is shear and moment function. So the design of a beam requires a detailed knowledge of the variation of the internal shear force B and the moment M acting at each point along the axis of the beam. The internal normal force is generally not considered for two reasons. In most cases, the loads applied to a beam act perpendicular to the beam axis and hence produce only an internal shear force and in bending moment. And for design purposes, the beam's resistance to shear, particularly to bending, is more important than its ability to resist normal force. So that is important. Why we are not including the internal normal force. So for the shear and moment function, what we will expect here is we will create a shear and moment function at each member for varying loadings. If there is no variation or there is no varying loading, we can have only one shear and one moment equation or function. So for example here, you have different loadings from A to B. It's uniformly distributed load. From P to D, BCD, it becomes concentrated load. So here we will have at least 3 functions, okay? Because there are 3 varying consideration. Here is considering the load, here is after the load, here is after the load of P. So I have 1, 2, 3, okay? So what are the procedures? The same. Determine the support reaction. Then shear and moment function specify separate coordinate x and associated origin extended into region of the beam between concentrated force or couple moment or where there is discontinuity of distributed loading. Section of the beam perpendicular to its axis at each distance x, and from the pre-body diagram of one of the segment, determine the unknowns B and M at the cut section as a function of x. So it's the same, B and M shown acting in their positive direction according to the one that we discussed a while ago. V is obtained from summation force along Y, and M is obtained by summing moment about the point S located at the cut section. Then the result can be checked by noting that the derivative of moment is V and derivative of V is uniform load. So these two are important to check whether we are correct or wrong. Let's have example. So determine the shear and moment in the beam as a function of x. So here we need to determine or create a certain functions that will represent the shear and moment. Okay? Here it's simply continuous distributed load. Although it's triangle but it is continuous, so we will have only one function. So first, determine the reaction. By the way, this is a fixed support, meaning it has shear, it has vertical force along x, y, and moment. But we will not consider anymore the internal normal force, meaning we focus on shear and moment only. So here, to determine the reaction here, we can do summation forces along Y. How? Summation forces along Y is equal to 0. This is $30 1/2. 30 times 2 is 30, right? Therefore, the support reaction here is 30. How about the moment? Get the summation moment at this fix. Assume any direction, clockwise or counterclockwise. So 30 times 20 is 600. So this is the moment. Now we can go to shear and moment function. So you can cut here at a certain location X. Then summation forces along Y. 30 minus 1/2 X 15 times X. How did we arrive with X over 15? If this is X, what is the load here? Let's say this is Y. Y over X is equal to 2 over 15. 2 over 30. So Y over X is equal to 1 over 15. So Y is X over 15. So this load is X over 15. Okay, X over 15. So now, summation moment at this point is 600 minus summation moment at the cut section is 600 minus 30 times X plus 1/2 X over 15 times 15 times X over 3. So moment is negative 600 plus 30x minus 0.011 x cubed. Now, to check that one, the derivative of moment is V and the derivative of B is the loading. Okay? So, what is the derivative of moment? It will become 30, then 3 times 0.011, negative 0.0333 x squared. It's correct, right? How about derivative of B? Derivative of B is negative 0.0667, which is equal to 1 over 15x. So we are correct. Okay? So that's it. I will upload another video because it's very difficult to upload a video with a very large data. Okay? Thank you guys for listening. I will upload a certain video that will present these examples. I will solve again using manual computation.